Hi, this is the lesson for Tuesday, August the 25th. You do need to complete the bell ringer, so make sure that you are going into your Tuesday folder for week 2 and that you're getting the bell ringer link and you complete your bell ringer. Today, we're also going to be using scissors and glue. Okay, so if you have some, go ahead and get some from your supplies. All right, so let's go ahead and write down the objective for today. Understanding the relationships of the real number system. So we have a real number system which includes all real numbers, but I'm going to kind of recap what you learned last year. But in order for us to start, I want to start with an activity. So work with a partner. In this case, we're going to work alone. Imagine an oval. One oval represents a set of houses in the United States. Another oval represents a set of the houses in Texas, and then the last one, the set of houses in El Paso. Label the ovals as USA, Texas, and El Paso, and place them in a way that correctly describes the relationship. So what I want you to do is go ahead and get a sheet of paper, like this, right? And you're going to draw yourself 3 ovals. So one's going to be the largest oval, the medium size, and the small one. And you're going to go ahead and draw them on your piece of paper, and then you're going to go ahead and cut them out. Okay, so go ahead and pause your video right now and go ahead and do that on your own. Okay, so you should be drawing your ovals, and you should be, once you draw them, you're going to cut them out. Okay, once you're done, go ahead and unpause this video. Okay, so now you should have your ovals, and they should be cut out. Now the next part is that we're going to have to label them. So let's think about how these ovals are in relationship to each other. So the largest oval, I think that one should be called the United States, right? Because inside of the United States belongs Texas. All of Texas is inside of the United States. And inside of Texas is El Paso. So all of El Paso should be inside of Texas. But at the same time, all of El Paso is also inside of the United States because it's overlapping all of Texas, and that all of Texas is overlapping all of the United States. So we're going to use something similar to this. We call this a Venn diagram. And we're going to use something similar to this when we're thinking about the sets of real numbers. So let's go ahead and remember something that we learned last year. So in your notes, you want to go ahead and write down counting. Okay, so the counting numbers are numbers that are like starting with 1, 1, 2, 3, and this number set keeps going on to positive infinity. So something even like the number 1 million would be considered a counting number, right? We just have to start at 1. We also have something called whole numbers. So the whole numbers, they are also including all of the counting numbers, but they have an extra element that the counting numbers do not have. The whole numbers start at 0. 0, 1, 2, 3, and on and on and on. So now we can kind of start to picture that, wait a minute, all of these counting numbers are also part of these whole numbers right here. The only difference is that the whole numbers have that 0 that the countings did not. Okay, now integers. Integers, I know you learned this about in 6th grade, and your 7th grade teacher talked to you about it. The integers actually includes all of these, but it's adding something to that. It's adding the negative, the opposites of these numbers right here. So the opposite of 3 is -3. The opposite of 2 is -2. The opposite of 1, -1. The opposite of 0 is 0. And it also is going to include the 1, the 2, the 3. So on and on to positive infinity, but also on and on to negative infinity. Now keep in mind that the integers are considered the whole numbers and their opposites. For example, something like -2.5 wouldn't be considered an integer because that is not the opposite of a whole number. That 0.5 is just not letting it be an integer. let's talk about those ones that are called rational numbers. Now the rational numbers we talked about last week, and we said that as long as it's a fraction, a divided by b, and b does not equal 0. That was our only condition. So for example, I can write something like example 4/5. But that's not the only one. What about 1/3? What about 7/4? That's also okay, right? What about the number 2? Is that a rational number? Let's see, can I write the number 2 as a fraction? Oh yeah, very simple, 2/1. What about the number -3? Is that rational? Oh yeah, -3 can be written as -3/1. So as a matter of fact, every single one of these counting is actually part of the rational. Every single one of these whole numbers is also a rational numbers. Every single one of these integer is rational. So really, the rational numbers are like this big set that includes pretty much everything. Not only does it include the counting, the whole, the integers, there's other numbers that are not part of those. Those other numbers that are not part of those are things like terminating decimals. For example, something like 4.6. That's a terminating decimal. It is rational, but it just doesn't get to be a counting, a whole, or an integer. But it is rational. Okay, another example would be something like -2.7. Or maybe like 0.613. Right? That's a terminating decimal. But the rational numbers also include the ones that repeat. For example, you know, like when you do 1/3, that's 0.333 repeating. Well, that's still a rational number. If it repeats, it's still rational, okay? Sometimes you have something like 1.151515, and then this is repeating, okay? That's still an example of a rational number. So these are like kind of like those numbers that get to be called rational, but they just don't get to be called any of these other ones over here. So how about we make a Venn diagram similar to the way that we did for USA, Texas, and El Paso. Let's do something similar to that, but let's do it with the sets that we just talked about right now. Let's do it with the counting, the whole, the integer, and the rational. So let's go ahead and make ovals for each one of those. So normally we would do this in group work, but we're going to go ahead and do it on our own. So you make one that says counting, one that says whole, integer, and rational. So this time I need 4 ovals, okay? So you're going to get another sheet of paper, and you're going to draw yourself 4 ovals. We're going to have the largest one, the second to largest one, the medium-sized one, and then the tiny little one. And we're going to start labeling them kind of like what we did with US, Texas, and El Paso. So go ahead. I'm going to give you 2 minutes to do that, and then come back. Okay, so go ahead and cut them out, and we're going to decide how we're going to label them. So we're back. So we have the largest one, the second to largest, the medium-sized one, and then the tiniest one. Now, if we think of those number sets that we just came up with, we said that the rational numbers actually included every one of them that we've seen so far in our notes right there. So for that reason, the biggest oval is going to be the rational. Okay? Now let's think about what should be the second biggest oval. Now, if I think about those notes that I just wrote right now, let's think about how specific they get, right? So for example, these counting numbers are very specific. Then this one gets a little bit bigger because it includes a 0. Then this one gets even bigger because it includes all of the counting and includes a 0, and it includes more numbers. So for that reason, I'm going to say the integers is actually the second to largest oval, right? So I first have the rational, and inside of the rational, all integers are rational. So I would place it like that. Then next would be the whole numbers, because the whole numbers, all of them are integers. All whole numbers are integers, so I need to go ahead and put the whole numbers inside of the integers. Oops, that's kind of hard. Like that. And then inside of the whole numbers, we still have the counting. So the counting are the ones that get real specific, right? So we're going from very specific to kind of like very broad kind of numbers, like very, very specific, only 1, 2, 3, 4, 5, 6, 7. Over here it's 0 and all of those right there. And then over here it's the negative whole numbers and all of those right there. And then the rational is all of these and the ones that are decimals and fractions and things like that. So this is how we need to go ahead and have our number set. Now this is when we're going to go ahead and get our glue stick, and we're going to glue our number sets together, and we're going to go ahead and get our notebook, and we're going to go ahead and glue it onto our notes so that we can have it there for us to look at. So we're going to get to our notebook, and we're going to glue it right there. Okay, so glue it onto your notes. All right, now let's go ahead and get started. So now that we have our number sets, now I need to be able to place my numbers in the right place. So let's start with something like the number 0. Now the number 0 is a rational number because in order for me to get to where it belongs over here in whole numbers. So I know that a 0 is a whole number, so it had to pass through the rational, it is a rational. Then it had to pass through integer, it is an integer. Then it had to get to whole number. Now I think to myself, can it be a natural number? And the answer is no. 0 is not natural, so I stop right there. That is where the 0 belongs. I shouldn't put it out here because if I put it out here, then I'm saying that it doesn't get to be called integer or whole. So it has to be right here, okay? Now let's try the negative 8.7. So negative 8.7 is a rational number, it's a terminating, but does it get to move on to integer? Now we said integers were negatives, but we said specifically they had to be negative whole numbers. So this has that 0.7, so that gets to stay out there. Okay, now the negative 5. Now the negative 5 is rational. Does it get to move on to integers? Yes, this time because it was an opposite of a whole number. Does it get to move on to whole numbers? Nope. Whole numbers doesn't include the negatives. Okay, so it stays out there. 3.6, it is rational. Does it get to move on to integer? Nope, I shouldn't have decimals in integers. Okay, what about 0.33333333? Wait a minute, is that rational? Yeah, we said that rationals can be repeating, so that is a rational number. What about 11? 11 I think has to go all the way to counting, or otherwise known as natural. So the number 11 is rational, it is integer, it is whole number, and it is a counting number. So the number 11 got to be part of all these layers, and it got to the most specific layer right here, so it's part of all 4 number sets. Okay, so let's go ahead and answer this question. It says, what number sets does the number 4 belong to? Now let's think about where 4 is in our 4 would be over here in natural. And in order for it to be a natural, it has to be all of these before it gets there. So right here, I'm going to go ahead and answer the number 4 is, it is rational, it is integer, it is a whole number, and it's also a counting, also known as natural. So number 4 got to be all of those. What about the number -2? Now, the -2 I think is an integer, but in order for it to be called an integer, it has to pass by the rational layer, okay? So it is rational, it is an integer. Does it get to move on to whole number? Nope, whole numbers doesn't include the negatives. So it's just those 2, okay? What about the number 0? Okay, so the number 0 is let's remember that it's a whole number. So in order for it to get all the way to whole number, it needs to have gone through the rational layer. It needs to have gone through the integer layer. And then it gets to the whole number layer. Does it get to move on to counting? Nope, it stops right there. That's it, okay? Now 1/3, is it rational? Yeah, it's a fraction. So it has to be rational. Does it get to move on to integer? Nope. That's it. That is it. That's it. What about the next one? Is that rational? Yeah, because if I write that as a decimal, that would be 1.4. And terminating decimals are rational. So this is rational. Does it get to move on to integer? Nope, because the integers can only be whole numbers and their opposites, in other words, negative whole numbers. Because of that decimal, that's it. So that's it. So that's how I use my my rational number diagram to tell where my numbers belong, and then I can tell what number sense they belong to. All right, so now all you have to do is work on completing the assignments on Nearpod and also the exit ticket. Okay, if you have any questions, please let me know.